a list of books that you should have noticed as you came in. I should have put it up at the end of the first lecture, but I've moved on to the second lecture, and if you missed that, I can put it up again at the end of this lecture. So now I'm moving on to a more detailed discussion of the principles of particle physics that I hope will clarify some of the things that I mentioned in the first lecture. And as I already mentioned, our understanding of particle physics rests on various tenets, basically two fundamental structures. Quantum mechanics, well, obviously, since we're probing at very short distances the properties of particles, we can't use classical physics. We have to use quantum mechanics. And symmetries. Now, symmetries are probably the part that you're less familiar with. And as we go along, I'll be developing how you deal with symmetries in more and more detail. But the symmetry that will be relevant to today's lecture will be that of relativity. Symmetries are central to our description of the fundamental forces. We have relativity, which consists of translations and Lorentz transformations, rotations, boosts, and something called Lie symmetries that I'll talk about in the fourth lecture, which are based on groups, special unitary groups, SU3, SU2, and U1. What we'll discover is that the group SU3 generates, if you understand its properties, it will lead to our understanding of the strong interactions and the fact that there are 8 gluons and 3 colors. The 3 is related to the 3 colors. SU2 will lead to an understanding of the weak interactions, the fact that you have an electron and the electron neutrino is related to that too. They belong to doublets of SU2. And the SU2 cross U1 together will lead to an understanding of the W plus, W minus, and Z gauge bosons, generating the weak interactions, and the electromagnetic interaction. So this is a very nice observation that once you've recognized the symmetries, you get the dynamics out. And that will be something to look forward to, I hope. So, application of symmetries, if you have a symmetry, or postulate a symmetry, the physics should be independent of your system of coordinates and units. So it shouldn't matter which coordinates you use, you should have the same symmetry. So as far as relativity is concerned, it doesn't matter whether you use x or x plus a to describe your x coordinates and so on. Special relativity is something I'm sure you have looked at. Space-time point is labeled by x, y, z spatial indices, and time as the first component. It's not invariant under translations, obviously. X goes to x plus a doesn't leave x invariant. So you can try and take a difference between two of these so-called 4 vectors, and a plus delta a minus a is delta a would be invariant under x going, all of x going to x plus a constant. But this, while that is invariant under translation, is not invariant under rotations or boosts. And what Einstein proposed was that the real invariant distance is not delta a, but delta a naught squared minus delta ai squared, where ai are the space coordinates. And we can write that in terms of a metric, g mu nu, summed over mu and nu from naught being the time component, 1, 2, 3 being the space components. So this is the invariant distance. And what Lorentz invariance means is that physics is invariant under all transformations that leave such distances invariant. They're translations and Lorentz transformations. Translations are obvious. In the Lorentz transformations, you've got rotations, but you also have boosts. The difference between rotations and boosts is that rotations act on the 3 space dimensions, boosts act on a space dimension and a time dimension. So for the moment, I'll leave special relativity as that, but at the end of the lecture, I'll come back and show you a few slides which make this more precise. Now, going back to the fundamental principles of particle physics, what one discovers is that if you combine quantum mechanics and relativity, and if you remember, Einstein always had problems with this. God does not play dice, he said. Well, apparently God does play dice. Quantum mechanics is correct. But quantum mechanics is incomplete because it doesn't include relativistic invariance. And when you put these two together, you get something called quantum field theory. And one of the most important aspects of these introductory lectures is to give you some feel for what it means to say field theory rather than mechanics. So let's try and see what's going on. There's fundamental division of the physicist's world that you can write in terms of speed, slow to fast. So in going from slow to fast, classical Newton theory becomes classical relativity, and special relativity is something you've already studied, and that's where the invariant length that Einstein introduced is relevant. Classical quantum mechanics becomes quantum field theory. Now, along this direction is something that you may not be familiar with, something called the action, which takes you, when the action is large, you have classical theory, Newton theory. When the action is small, you go to quantum theory. So what is the action? Well, the action, if you're going from a point A to a point B, the action is the integral from, with respect to time, from time at point A to the time at point B of the kinetic energy minus the potential energy. Not something that's obviously relevant. And in going from A to B, there are many different paths that you can take. The action is something that we will use in subsequent lectures. It's given by the integral of a Lagrangian with respect to time. The Lagrangian is the kinetic energy minus the potential energy. So the Lagrangian is what's sitting under here, the kinetic energy minus potential energy. And for non-relativistic mechanics, this is how you define the Lagrangian. When we go to relativistic mechanics, it won't make any sense to have just an integral with respect to time. We'll have to include space, but we'll come back to that. Now, what one has found is that quantum mechanics can be defined as a sum over all paths, where that means you sum over every way you can get from A to B, but you weight each path by a function of the action. So you have a linear sum. Each path has a weighting. And the weighting is proportional to e to the I s over h, s being the action, h being Planck's constant. And the fascinating thing is that the classical path that leads to normal mechanics, the equations of motion, is the path that minimizes this action. It's called the principle of least action. And if you're not familiar with action, there's a beautiful lecture in the Feynman Lectures in Physics, Volume 2, Chapter 19, that I recommend you have a look at, where he discusses how he first met this concept and how it works to derive the classical path from the minimization of the action. I don't have time to go through all of that, but if you are interested, there's a good reference. Now, why do we like to formulate quantum mechanics in terms of an action? Well, the action, as we see, is written in terms of a Lagrangian, and the beauty of this is that the Lagrangian is invariant under all the symmetries of nature, which means that it's very simple to if you have an idea for a symmetry, it's very simple to implement what the implications of that symmetry are by constraining the form of your Lagrangian to be invariant under those symmetries. And we'll use that fact as we go along. So at the moment, these are just general ideas that I'm throwing at you, and we'll come back and use them. And now, to explain this diagram, we have the quantum mechanical amplitude is e to the I s over h, where s varies depending on which path you take, because depending on the paths, the kinetic energy minus the potential energy, or the potential energy minus kinetic energy can vary depending on how you get from A to B. And you weight it by this factor, e to the I theta, a complex number. And as h becomes small, this phase oscillates much more quickly. You can imagine if this is the classical path is the one that minimizes the action. It's a turning point. So the action is varying rather slowly as you go to either side of it. But as h tends to 0, even a small change in the action gives you a huge change in the phase. And you're adding all of these paths together, so you get destructive interference, which is why the one that is dominant is the one which minimizes the action. It's one with the least destructive interference because s is varying most slowly. Out here, it will be varying rapidly, and it will give you a very small contribution to the action, to the path, because an adjacent path will cancel it. All of this is explained in the Feynman lecture that I referred to. So as h becomes small, you can't just use the classical path. You have to worry about all the other paths, and you go from large action to small action, and you have to go to classical mechanics. So this is a two-dimensional space explaining in what region Newton's classical Newtonian mechanics applies. Slow system, large action, or essentially h going to 0. Here, h going larger, you have to worry about larger variations of the action. It gives you classical quantum mechanics. And then, as you go to a relativistic theory, you change the quantum mechanics to the field theory, just as you change Newtonian mechanics to relativistic mechanics. Just as amusement, you can generalize this a little bit. So-called Bronstein cube of theories. This is slightly inverted with respect to the directions we had. Now the non-relativistic quantum mechanics is sitting up here, whereas before it was down here, and Newtonian classical theory is sitting down here. But this face of the cube is what we just saw. If we go to the relativistic case, we go to special relativity from the Newtonian theory, and quantum mechanics becomes quantum field theory. But the cube has added an extra dimension, which is switching on gravity. Essentially, if I make this gravitational constant 0, I'm switching off gravity. I don't worry about it. But as I make the gravitational coupling, Newton constant, non-zero, I'm switching on gravity. And you go from special relativity, let's start from this point, becomes general relativity, Einstein's theory of general relativity. So this axis is where you worry about that last force, the gravitational force. And this is where much of the current work in theoretical physics is aimed. It's trying to understand how you go in this dimension. So one promising way is to start going into the non-relativistic quantum mechanics. We switch on we go to fast systems and switch on relativistic effects, and you go to quantum field theory, which is the subject of these lectures. But if you switch on the gravitational interaction, you go to a theory of gravity, and the most promising one, perhaps, is string theory, and there will be some discussion of where that goes. So this is trying to put into context where we are in these lectures. I'm on this plane, on this face of this cube, but ultimately we'd like to get to this point. So going back, quantum field theory. Why do we need quantum field theory? Well, quantum mechanics is a quantization of a dynamical system of particles. And the difference between that and quantum field theory quantum field theory is an application of quantum mechanics to a dynamical system of fields. And to date, I haven't defined what a field is. It's different from a particle, and we'll have to see what it means. Let's look at some of the drawbacks of quantum mechanics. Probably you haven't seen many drawbacks of quantum mechanics. They seem to work rather well. But if we are in a relativistic situation, we have a conversion possible between energy and mass, E equals mc squared. And what that means is if you get, for example, to an energy greater than twice the mass of an electron, I can convert that energy into a pair of electrons, or electron and positron. So once you get to these high energies, you have no right to talk about things as being a single particle, because you must allow for the possibility that the single particle becomes a single particle plus an electron-positron pair creation. And this is not in quantum mechanics, but it will be in field theory. And what the field is doing effectively is to describe a state. It will be a single particle, but it will also describe a single particle plus a pair created with a single particle, if you're at the appropriate energy. So the field can describe simultaneously multi-particle states. Second, and probably more convincing explanation as to why you need to go away from quantum mechanics is that relativistic quantum mechanics has physical problems. In particular, it violates causality. And actually, with elementary calculation, you can see that it doesn't conserve causality, because if I want the amplitude for free propagation from x0 to x, what I do is I start with my state, my ket at x0. It evolves like e to the minus iet, e being the energy. If this is non-relativistic, it would be p squared over 2m, where p is the momentum. And then I look at the overlap with the state x to get the amplitude going from x0 to x. Here I've just inserted a complete set of states, of momentum states, which means that the result, after noticing that energy momentum conservation forces p prime to be p, is an integral over d3p. Here's my factor e to the minus p squared over 2mt. And then the overlap xp, p x0 gives me e to the ip x minus x0. And finally, I can do this integration over the 3p momenta, and I get something that looks like e to the im x minus x0 squared over 2t. It's a Gaussian integral. It can be done relatively easily. The important thing is this is non-zero for all x and t, which means that it doesn't vanish outside the causal cone. So you get an amplitude of going from x to x0 even though it goes faster than the speed of light. So it violates causality. And clearly, if you have a hope to respect causality, you have to go to the relativistic theory. But even in the relativistic case, when you do the calculation for quantum mechanics, you find it remains non-zero for all x and t. So quantum mechanics by itself violates causality. And what I'll have to convince you at some stage is that when we go from quantum mechanics to quantum field theory, the new aspects of quantum field theory restore causality. Okay, that's for the future. Let's go back then, starting with quantum mechanics. Classical non-relativistic theory, E is equal to p squared over 2m, kinetic energy. When one goes along the h bar to small route, we have to replace E by minus I h bar d by dt, and we end up with the Schrödinger equation. I h bar d phi by dt and the second part, I've replaced the momentum by h d by dx, d by dy, d by dz. So I get del squared entering here. This is a quantum mechanical analog of the classical equation, the Schrödinger equation. What about the case that we go to the relativistic quantum mechanics? Here now, the equation of motion becomes e squared equals p squared plus m squared, or e squared minus p squared equals m squared. Here I'm being a particle physicist and gone immediately to natural units. So I've set c equal to 1, and h bar in the next equation will also be equal to 1. So I'm in natural units. It just makes it much easier to write down the formulas rather than keeping mc squared c to the fourth, etc. Quantum mechanically, this equation, you just do the same as you did before. You replace energy by minus I h bar d by dt, so I get a minus d2 phi by dt squared, where phi is the single particle state that you're operating on, plus or minus del squared phi coming from this p squared term is m squared phi. There's an I squared that enters on the left-hand side, so that's why the signs have changed. And this is known as the Klein-Gordon equation. Actually, it was written down first by Schrödinger, but then Schrödinger discovered the problems that I'm going to talk about in just a moment, and went back to the non-relativistic equation that we saw before, and that describes rather well many of the properties of the atom. And Klein and Gordon were the ones that really first published this. Here is Klein. You'll find later lectures he's also been responsible for these new and exciting ideas that space may not be four-dimensional, but it may be multi-dimensional, and the extra dimensions are curled up. So this is representing a flat dimension, and this is a curled-up dimension. Anyway, the Klein-Gordon equation refers to the behavior of a relativistic quantum mechanical system for a scalar particle. That means it's got spin 0. Simplest possible state you can imagine. And here's the Klein-Gordon equation rewritten. If I look at the energy of this system, I take the square root of this, and I get the energy is plus or minus square root of p squared plus m squared. Here's where the problem occurs. How do you interpret a negative energy state? Does it make any sense? In 1927, Dirac, looking at the Klein-Gordon equation, said, we want to get rid of these negative energy states. They don't make any sense. And he wrote a relativistic equation which didn't involve E squared, it just involved E. And in doing so, he discovered the need for fermions. Electron, for example. And, I mean, that's a very fundamental contribution to physics. It turns out that his original motivation was incorrect. Namely, he actually didn't achieve the elimination of the negative energy solutions because the Dirac equation has negative energy solutions. We often interpret it as a filled sea of electrons in which you've got the electrons above the Fermi level. But there are negative energy solutions in a very fundamental way there. So wrong motivation but correct result, 1927. Physics moved rather slowly then. There weren't so many physicists, and it's a difficult problem. But you shouldn't ignore a underlying problem. And in 1934, Pauli and Weisskopf revived the Klein-Gordon equation, which had dropped into disrepute because of this problem. And what they did was they reinterpreted the negative energy solutions as positive energy solutions for particles of opposite charge, antiparticles. This turns out to be the correct interpretation, and you'll see in some detail in the equations that I write down how this interpretation can be justified. But what this actually means is that in this case, the field phi, as it now becomes, because we're writing a relativistic theory, and phi now is not a single particle state, but it can describe pair production. It also describes antiparticles. So one of the important contributions of field theory is the understanding there have to be antiparticles and the ability to use a single function of space and time to describe both the particle, the antiparticle, and the multiparticle states. Unlike Dirac's whole theory, which is this filled sea of negative energy states, this interpretation is applicable to bosons, i.e. integer spin 0, spin 1. as well as to fermions, spin 0, spin a half, spin 3 halves. So this is what we will come to understand this Pauli-Weisskopf reinterpretation of the negative energy states. And as you will see, the antiparticle states that you include with this interpretation are very nice in the sense that that violation of causality I showed you earlier is removed once you realize that in calculating the propagation from x naught to x, you should have included the effect of the antiparticle states. And that then makes the theory causal. Another reason to have faith that you're on the right track. So now, moving on, let's get a physical interpretation of quantum mechanics. We have the Schrödinger equation, the non-relativistic case, and I'm sure you've gone through this exercise, but to get a physical interpretation, what you can do is to take this equation and multiply it by the complex conjugate of this field phi. Phi is a complex field. So take the complex conjugate phi star times the Schrödinger equation and subtract from it phi times the complex conjugate of this equation. And it's only a matter of a couple of lines of algebra to see that it can be rewritten in the form of what's known as a continuity equation, where the rho and the j, rho is phi modulus of phi squared, j is given by phi star del phi minus phi del phi star. This is a continuity equation in the sense that if I integrate it over a volume, then the integral of d rho by dt over that volume tells you the change in rho in a given time in that volume. And you use the divergence theorem to take the right-hand side and rewrite an integral of del dot m dv as an integral of m dot n ds, where n is the normal. So this is a flux going through the surface. So with that understanding that this is a continuity equation, it's exactly the type of equation one finds in hydrodynamics. This is how you make a physical interpretation of it. You realize that you can interpret rho as phi squared. In quantum mechanics, phi squared gives you a probability. This will be a probability density. So you're integrating the change in a probability density within a volume. And J will be the probability current, the flow of probability through the surface in this way of looking at it. So this is the way we interpret Schrödinger equation. We have a probability density and a probability current. If I did the same for the Klein-Gordon equation, and I hope you've already met in your quantum mechanics this concept, it's very straightforward. You just go and repeat the process that got you to this continuity equation. You multiply the Klein-Gordon equation by phi star and subtract phi times the Klein-Gordon equation star, and you end up with a probability density, which is slightly different because now we've got a second order derivative with respect to time, whereas previously we had a first order. So you get a phi star d phi by dt rather than the phi squared on its own. And the second piece is just as we had before, so the current is exactly the same form as we'd got before, where these derivatives are acting on the three spatial indices. So you can see you're just restoring the symmetry between space and time. And so the probability density has the same structure as the probability current, except it's a derivative with respect to time rather than space. And then with that understanding, you realize that you can put these two components into what a 4-vector, a J mu, in which the first component is the probability density, and the remaining 3 components are the probability current. So this is a relativistic generalization of probability density, probability current. What about the solutions to the Klein-Gordon? Well, a free particle solution, if you just put an e to the I p dot x, the dot refers to a 4 contraction, p mu, x mu. I'll come to that in the next slide. So it's a 4-vector invariant, p dot x. And substituting that in here, you find that you get the equation p squared minus e squared equals m squared. because when you take d by dt, you take d by dx naught. P naught is the energy, so that brings down the E squared. D by dx will give you the momentum, P. That will give me then summing over the x, y, and z gives the P squared. So this is E squared minus P squared equals m squared, a relativistic equation. And this is a solution to the equation. N is a normalization constant. And just substituting this solution into rho, you find rho is given by its derivative with respect to time, so you get an energy times n squared, where n is just a constant. For convenience, and this is a relativistically sensible thing to do, we can normalize n such that the integral over rho over a volume is twice the energy. And if I do that, I end up with what are called the normalized free-particle solutions, e to the plus or minus I p dot x, where I've now allowed for the fact that since we're working with a quadratic equation, it doesn't matter whether I got plus or minus, divided by the square root of 2 times the energy times the volume. If I integrate this in here, I get twice the energy. So these are the normalized free-particle solutions that we'll use. So this is the structure of the Klein-Gordon equation. This is the structure of the probability density. It looks similar to the probability density that we obtained for the Schrödinger equation, except we have an energy sitting outside. And that's where the trouble happens. If we've got negative energy, then we seem to have negative probability. And negative probability doesn't make any sense. This is why, after Klein and Gordon wrote down their equation, Dirac and others looked for an alternative because they couldn't live with this negative probability. Okay, I seem to be going a little bit faster than I expected, so I have a little time to talk about some of these transparencies with a red rim, which is essentially, I know there's a variety of interests in the audience, and some of you will not be interested in the details, and some will be. One of the important aspects in developing this is the understanding of group properties. And here I have put in a few transparencies which explain to you how the Lorentz symmetry can be related to an underlying Lorentz group, which will be important in the study later on. So here are the Lorentz transformations. What is required is Einstein said that the invariant length, x naught squared minus xi squared summed over I should be invariant, an invariant length. So we look for a transformation which is characterized by lambda acting on the coordinates x nu. So x is the 4 vector, x naught is c times t, xi is x, y, z, and when I write something like this down with a contracted index, nu, Greek index, it means that you sum between 0 and 3. So this is really lambda mu naught x naught plus lambda mu 1 x1, etc. And mu itself can run between 0 and 3. The statement that the length should be invariant means that if I go to this transformed system, lambda is supposed to generate a Lorentz transformation, and it gives me x primed. G mu mu x prime nu should be the same as g mu mu x mu x mu. The summation convention is assumed. Namely, in here, I'm summing between 0 and 3, both on the mu index and the nu index. Substituting this result in here, you immediately get the constraint on these constants lambda mu mu, where this is a matrix with a row and column indices mu and nu, such that this should be true. And then you sit down and ask what satisfies this condition. And the answer is you get 3 rotations. Now you should be on more familiar ground, acting on this 4 vector x mu, which is ct x, y, z, written as a column vector. R is a 4 by 4 object. That's the lambda nu nu. It's got 4 rows and 4 columns. And if it's a rotation about the z-axis, it can be written as a cosine theta, sine theta, minus sine theta, cosine theta in the middle entries with ones at the side. Multiplying that out, you see that it does just what a rotation does. So this rather more formal definition of lambdas becomes something that you can see rather straightforwardly in terms of explicit constructions for this rotation matrix. Now, those are rotations, but the Lorentz group also involves boosts, and the difference is here, if I put a rotation here about the z-axis, it acts on the 3 by 3 block down here, which has no time component. So I could have had a rotation about the y-axis, it would just have changed where I put the sines and cosines. But when I put it in a block involving the first row and the first column, I get something that's a boost. The difference between space and time is that you have a minus sign in the metric for the spatial indices and a plus sign for the time, and that effectively means that you're doing a rotation with an imaginary theta, and that changes it. If I write theta equals I alpha, cosine theta would be cosh alpha. So these are the boosts, and what you have for the Lorentz group are 3 rotations and 3 boosts. And then finally, you can check that there are 2 special cases. There's space reflection, in which you reverse the sign of the spatial components. That clearly will leave this invariant because it's quadratic in the spatial components, and this is something that's called parity symmetry. And there's another one where you reverse the sign of the time component, and that also leaves this invariant. So these are the elements of the Lorentz transformations, and with postulators, the Lorentz transformations leave physics invariant. Now here's the new aspect. The Lorentz transformations form a group. And again, I stress that those transparencies in red are ones we're getting a little bit more technical, and it's not essential that you follow this to follow the remainder of the lectures, but those of you that are interested can go through the details that you'll find on these transparencies and check that you understand it. The Lorentz transformations form the group SO31. Now what that means is, first of all, a group property, if you have 2 group elements, G1 and G2, that might be 2 rotations. The product of 2 rotations should also be a member of the same group. 2 rotations is still a rotation, so that's rotations themselves form a group. But a rotation times a boost is a boost, so it closes and forms a group. That's a group property. And another interesting thing is that you can represent a group element, such as our R, that I wrote down on the previous one for a rotation about the z-axis. Lost my pointer. You can write that. I can't see another pointer. Oh, this is a pointer. Yeah. You can write this in an exponential form, e to the minus I j dot theta over h bar, where j is the angular momentum operator. Theta tells you how much you're rotating about the z-axis, if I chose j to be the z-axis. But more generally, theta could be in the y or z direction. And associated with the fact that r's form a group, the j's form what's known as an algebra, where you take the commutation relations, ji, jj minus jj, ji, and they have to give you another j. These are the generators of the group. The ji are the generators of group SO3, which is the group of rotations, because I'm here writing the rotations only, but if I extended that to include the boosts, I would find that they would generate the group SO31. Now, I don't want to go into the details, but if you're interested in seeing how this actually works out, or in this transparency, if you're interested in seeing how you prove that the generators form a group, this is what is being done here. I just multiplying for small rotations. These are the theta. Theta I've chosen to be epsilon, where epsilon is a small number. Similarly, theta I've chosen to be eta, where eta is a small number. Doing this, you can show that jx, jy is I, jz, which is what we had in the previous transparency. I won't go through it anymore, but these transparencies will be on the web, and you can check them for yourself. The demonstration that I can write a rotation about the z-axis as e to the minus I jz theta is also relatively straightforward, but requires that you sit down with a pen and paper and go through it. Jz is an angular momentum operator, and it can be written as x d by dy minus y d by dx. If I substitute that in there, I want to show that it's equivalent to a rotation in the form that we're familiar with a cosine sine minus sine cosine acting on the x and y. So I work for small theta, and I check that indeed expanding this as 1 minus ijz theta operating on my function of x and y, I get the appropriate rotation. So this is a demonstration that you have this exponentiation property. The previous transparency then showed that the group elements satisfied commutation relations. And the final one is just putting it all together and checking indeed explicitly that the form that we had before can be written as e to the I jz dot theta, where jz has this structure in matrix form vector notation. So some things are difficult to follow just on the screen and need you to go through it a little bit more in detail. I hope there's enough detail at least to support what I showed you there. And there I'll leave it. Thank you.